Talk about why we integrate. Okay, in order for us to do that, we're going to investigate we're going to do some physics. Apologies for those who don't do physics. But it's just the easiest way to explain it. Okay, so here's my question. All right, and again, you physics students should know this in your head, so just keep it on the down low for a moment. Okay, but if I travel, let's say I travel at let's say 20 metres per second for 5 seconds. Okay, so if I travel at 20 metres per second for 5 seconds, right, how far do I travel? So what is my position at the end of that time? Right, so how far have I moved away from my starting point is my first question. The 20 metres per second for 5 seconds, how far have I moved? Pardon? Oh, I don't mind. 100 metres? Pretty easy? Yep. Okay, so what if I was to graph that? Right, so if I was to graph that scenario, right, so there's my time, okay, and there's my velocity, right, and I was to graph that, what would that graph look like? Yep, go on. Nope. No, it wouldn't be. So yeah, my velocity's not changing, is it? So it's starting at 20 metres per second, and it keeps going at that, right? So it comes across here, and then if I stop that at 5 seconds, so let's say I start at 0 and I go to there, then I've basically got the graph of that motion. Does that make sense? Yep. So we've already calculated that I know that if I want to find my displacement or my position, okay, don't use the mean symbol, Greg, okay? So in mathematics, we talk about position being x. So where are you? X marks the spot. So in physics, position is synonymous with displacement. Okay, so we've talked in this class a little bit about displacement versus distance. Okay, distance, how far you travel, displacement, how far away are you from your starting point. So in maths, displacement is the same as position. So what position are you in? So we give it the symbol x, okay? And so that's going to be something that you're going to need to get used to. So if I want to calculate my position, it's going to be how fast did I travel, and you multiplied it by 5 seconds, and that got me my 100 metres. Okay? So I've travelled 100 metres. Is that okay? Right. On the graph, right, so just zoom in just a little bit. On that graph, what characteristic of the graph gives me the same information that I just calculated, 100 metres? So if I was to look at that, what characteristic of the graph gives me that position? The area, yeah. So if I was to shade in this area here, right, that's a rectangle with a length of, depends on which way you go, length and width, but let's say a length of 5 and a width of 20, okay? So its area is 100 metres. Is that okay? We call that? Okay. So what we're going to be investigating is this relationship between this idea of area and how it works with integration. Okay? And so we're going to look at, well, how do we do that? All right? And so if I was to make this a little bit more complicated, just a smidgen more complicated, okay? And let's say I start at 10 metres per second, all right? And then I accelerate at 5 metres per second every second for 3 seconds. Okay, how far have I travelled? In 3 seconds. Okay, so I start travelling at 10 metres per second. I accelerate at 5 metres per second every second for 3 seconds. How far have I travelled in 3 seconds? So there's a number of ways. So if you're a physics student, you will know that there's a formula for that. Do you agree with that? There's a formula, yeah? Okay, so what would that formula be, physics students? And math students and not physics students, you do not have to know this formula for any second, all right? Don't feel like but I just want to link everything together, okay? So what would be the formula to calculate that? Right, S equals UT plus 1/2 AT squared. Is that fair enough? And you can, now so if I put it in math speak, right, we wouldn't use S, we'd use position, okay? What does the U represent? Initial velocity. So in this case it's 10, okay? T represents time, A represents acceleration, okay? And you could substitute that in there and you can find that piece of information. Is that all right? Okay, so, but we're going to pretend in our subject, and it's not a pretend for some of you, you've never heard that formula before. Okay, for two of you, you've never heard that formula before. Do you do physics? I can never remember. No, that's right. So and obviously you don't either. So that for you two is what? Correct? Have you ever seen that before? Eli?
I did physics in grade 10.
Yeah, in grade 10, yeah. So you might have covered it in grade 10, but it's unlikely. We don't usually go that far, and it's completely foreign to you, right? Yeah. Good, that's fine, because there's no expectation that you will use it, right? Because we're going to get to this. Okay, so let's rub that out. Let's pretend for a moment that doesn't exist. Oh, by the way, if it, what I should have done is we use that formula, it'll be 10 multiplied by 3 plus 1/2 times 5 times 3. And so what do we get as a solution? Just so we've got a number in our head. So it's 10 times 3 is 30, half of 15, 7, so 37.5 metres. Are we okay? Oh, it's 3 squared, it is too. So 9 5s are 45, half of 45 is 22.5 plus 30, so 52.5. Have I got that right now? Cool, okay, so we've travelled 52.5 metres. So we've got that number in our head, right? Let's do a similar idea. Ignore what's below that, we'll get into that in a minute. So let's draw what this might look like, okay? So let's draw this idea. So let's talk about it in terms of velocity and time. Okay, so if we were to draw this graph, we're going to start off at 10. Okay, and then after each of our seconds, so we've got second number 1, second number 2, second number 3. So remember, we're accelerating at 5 metres per second every second. Okay? So after 1 second, how fast am I now travelling? 15 seconds. Okay, we're starting at 10, we're accelerating at 5 metres per second every second. So after 1 second, I've got my velocity's increased by 5 metres per second, so now I'm going 15. So starting here, then I go 15. How fast am I travelling after 2 seconds? 20, right? And then how fast am I travelling after 3 seconds? 25. Okay, so that's, graph is really bad. So let's just try and make it a bit better. Okay, so what I've in fact drawn here, we're going to pretend that's a straight line because we've got a constant acceleration. Oh, acceleration.
Is that just
Yeah, so acceleration is, so if you think about, yeah, let's break it down a bit, right? So if you think about what is, so if you're driving it?
Yeah.
Yeah, okay, so you put your foot down, what happens? Right, what does that mean? You're going faster. So every second, right, so if you think about velocity, right, velocity is measured in metres per second. So it's how many metres you travel every second, right? So that's its units, metres per second, okay? Acceleration is the change in velocity, right? So change in velocity is I'm going to travel 5 metres, I'm going to change my velocity by 5 metres per second every second. So the second S in that is the change in the velocity of the first. So this, if you like it here, this is your velocity per second. So there's another way. So physics students typically write that as 5 metres per second squared. Right? That should be familiar to you. Yep. And sometimes, depending on, oops, I'll see it with index notation. Right, so that's, but we're not going that deep. We don't need to. Okay, so just so you know it's available. Right, so if we see that graph, we've got a straight line. Okay, now let's use the same concept that we tried here, that displacement is the area under the curve. Right, so if I come across here, I want to know the area under there. So, what shape is that for a start? Yeah, or mathematicians would call it a what? Trapezium. Yeah, trapezoid, trapezium. Right, it's a trapezium. A trapezium is a shape with two parallel sides. So one pair of parallel sides. Okay, so we've got one side, two sides are parallel, and those two parallel sides are a distance apart. Is that okay? So can you remember what the formula for area of a trapezium is?
Half of A plus B times H.
Yep. Okay, A and B are my parallel sides, H is my height, distance between them. Okay, so I've got a half. A and B are the heights of my parallel sides, so in this case it's going to be 10 plus 25. And then multiply that by the height, so that's the distance they are apart, which in this case is 3. In order to do that calculation, so 10 plus 25 is 35. 35 multiplied by 3 is 105. 105 divided by 2. I know, it's going to come as a real shock to everybody. It's 52.5 metres, right, which is what we calculated with the formula over here. Okay? Let's just be really tricky right now. Is that okay with everyone? Let's be really tricky. You guys should already know this from specialists, so just hold this piece of information to yourself for a moment. Okay. If I was to ask you, actually no, I'll do this one, right? So what is the equation of that line? It's a linear equation. So here's my question. Actually, you can all do this, whether specialists or not. So there's my graph. Right? It's a straight line. I want you to tell me what's the equation of that line. Y equals, or in this case, it'll be V and T are your variables. Okay? What is the equation of that line? Don't overthink this. It should be as simple as it sounds. We should all have an equation, do we? What's the one? So what's the equation, Cindy? What have you got?
V equals
5 over 1t.
Yeah.
Yep, so just 5t. Yep, plus 10, that's fine. Yeah, perfectly fine. Yep. So the gradient's 5. Goes up 5 for every 1 across. If you wrote 5 or 1, that's perfectly fine, right? But we don't need to, right? So 5t plus 10. Y-intercept is 10. We all good with that? That should be really, really straightforward now. Now, here's a question for you. I want you to integrate V with respect to T for me. Now, this is something that you have been doing, right? Integrate that equation for me, please. So you've got 5t plus 10, integrate with respect to T. Do we agree with that? 5t squared on 2 plus 10t plus this integral constant c? Yeah? Do we agree with that? Does that seem okay? Yep. So let's just rewrite that in a slightly different way. Is that all right? So I'm just going to write 10t plus a half times 5t squared plus c. Okay? Well, plus, let's deal with the plus c first before we look at the rest of it. So, plus c. Now, if I go back to the problem that I've given you, I want to know, again, what c is. Okay, I want to know what the integral constant is in this question. So my question is this. Pardon me. So I need to know, so I know my velocity at time t equals 0, but I've just found the integral of velocity. So I've got this equation which has got 10t plus a half times 5t squared plus c. So first of all, we need to identify, well, what is that equation giving us? What information have I just got there? Anyone, any thoughts? What does that equation give us? So I've integrated velocity. It's the position. Now, how do I know its position? Well, first way I know is, you might recall, I rubbed it out and I probably shouldn't have. Let me go back to this. And I wrote the bloody mean symbol again. It's a habit. Going to get out of that. So this was the formula that we had. ut plus a half times a times t squared. Now, u is my initial velocity. In this question, what's my initial velocity? 10. So I can replace the u with a 10. What's my acceleration? No, it's not. It's 5. Right, so I'm going to replace the a with a 5. So hopefully you can see that from there I've got exactly the same equation. 10t plus a half times 5t squared. So therefore I need to work out what my c value is. So this equation, by integrating velocity, I've now got an equation for position. Okay? Similarly, if I differentiate position, velocity is the rate of change of position. Rate of change means derivative. We've done this in the past. Right? We've done that relationship. If I have position, I define its derivative, that gives me velocity. If I have velocity and I define its derivative, that gives me acceleration. So we've done that last year when we first looked at derivatives as an example. Okay? We haven't done it in a while, hence this. So now I've got an equation for position. Can I find a value for c? So looking at the data that I've given you, is the graph or the question, what do I know about its position? Do I have any information or any information I can assume for this question? What's its initial position, if you like? Where does it start? Zero. How do I know that? Or do I know it or am I assuming it? I'm actually assuming it. I don't know for 100% fact, but I'm not given any other information. So what I'm thinking to myself is, so I calculated how far I travelled in those 3 seconds. That was my question, right? If I travelled, how far do I go in those 3 seconds? Then all I basically know is if I know what my starting point is, I know how far away I am from that, then that tells me how far. So I can make the assumption that I'm starting at 0. Some questions will give you a starting position. You're starting at -5, you're starting at 10 or whatever, right? But in this question, we're not told. So we can assume that at t equals 0, the position is 0, therefore c is 0, which gives me my equation, ut plus a half at squared. So that's where it comes from. Okay, so why all that? What's the point? So what my point is that if I can find the area under the graph, that gives me the integral. Okay, so the whole point here is that integration is area under the graph. Okay, now that's all well and good. That's all well and good if the graph is a line. Because I can find areas, of triangles and rectangles and, you know, that sort of shape. I've got formulas for that. But what happens when it's not? Right? What happens when it's a curve? If I want to find the area under a curve, right? So if I have an a velocity, don't want that, turn that off. If I want, I'll rub this out in a minute, but if I have a velocity curve, right, velocity and time, and my graph does this, all right, so it has the velocity is related to time following an exponential graph, right? And I want to know, well, what's my displacement, what's my position from t equals 0 to t equals 5, for argument's sake. And I want to know that area there. How on earth do I do that? Because it's not straight. I've only got formulas for straight lines. Well, and that's what we're going to look at. So there's lots of ways you can do that, okay? And so what we're doing is this, okay? So there are lots of ways that you can find area under a curve, okay? But notice the key word there is estimating, right? Estimating, all right? Now, for our particular purposes, I'm going to show you what I'm talking about with left endpoint and right endpoint rectangles and what that means, okay? But for the sake of your exam, the only one you're going to be assessed on is the third one, which is the trapezoidal method. Trapezoid, we've come across that already today, okay? In specialists, you guys will do another method called Simpson's rule. It's very similar, just has it's a bit more accurate depending on the function, right? But it's not much more difficult. So we're going to focus on these numerical methods of area. So this is what people would use in the real world, right? So a real world example. Yes, sir?
Do we have to use that whole huge formula?
I don't know, what whole huge formula?
What is it? Sn equals delta x on 3x plus 4.
Here's Simpson's rule, Jim. Yes.
Oh, no.
It's also given, yeah, it's not hard. It's really not hard.
It's less hard.
But once you break it down, trapezoidal rule is not much easier. So, okay, but it is. Once you see it, it's actually hard, and easy, and we're going to use our calculators to do most of the work. Okay, our calculators do most of the work, we just got to understand what's going on. So we're going to build towards this, okay? So we're going to estimate area. So this is used so the trapezoidal method particularly is used in excavation. For example, if you have to cut out a whole section of a mountain, okay, it's very difficult to actually work out what the graph is of the curve of the mountain, right? Because volume is area times depth, right? So if you can work out the area and then multiply it by how deep it goes, you can work out volume, okay? But working out the equation of a mountain is quite challenging. But you can use this idea and approximate the area and get it to accurate enough that you can deal with it in excavation, as an example. All right, so we're going to look at the situation when we do what are called left endpoint rectangles and right endpoint rectangles. Okay, so let's have a look at an example. So what we've got here, if I can get across, right, there it is there. Here's an example of an equation. Okay, so f of x equals 9 minus 0.1 x squared. So there's my function. It's not a difficult one, it's a parabola. Okay, and I want to find the area that's shaded. Now this is the example that we'll use when we get to the trapezoidal rule shortly. Okay, as a way of introducing that idea. But before we do that, I want to talk about what does this left endpoint, right endpoint idea mean. Okay, so I'm going to redraw that graph without the shading and without the trapeziums. Okay, so again, we're going to do down here. So let's draw it in. Oh, that's not useful. Undo. Let's try that again. Okay, so we'll draw the function in. Okay, so there's my graph. I'll just make it nice and big to see. So we've got y, x. It will cross the graph at some point. Okay, so we know that if this is my function, f of x is equal to 9 minus 0.1 x squared. My y-intercept is 9. All right, so we know it crosses the graph at 9, not very hard. Okay, and we're going to be looking at what is the area under the curve from x equals 2 to x equals 5. Okay, I want to know that area there. Okay? So if we were to do left-end rectangles, what the heck does that mean? So first thing I'm going to do is I'm going to break up my area into evenly spaced, that's not very straight, let me just move that across a bit. So I'm going to break it up into evenly spaced rectangles. Okay, now if I'm going to make a rectangle, then I need to actually make a rectangle. So the left-hand rectangle simply means I take from each left-hand point, so each of those grey dots, I'm going to create a rectangle. So there's my first rectangle, right? There's my second rectangle, and there's my third one. Now let's assume they're all evenly spaced, okay? Because obviously, not really, but we get the idea. Okay. Now, am I able to find areas of rectangles? Yeah, of course I can. So, here's what I want us to do. What is the height of the first rectangle? It's not 9. Did you say 9? No. In other words, what's this point? What's the coordinates of that point there? Yeah, 8.6. So let's grab our graphics calculators out. We're going to save ourselves some time, and we're going to do this with our calculators. This, by the way, you will only be asked complicated questions in your calculator with this. So just bring my calculator into the screen. Come on, move. There we go. Okay. So we're going to make our life a bit simpler. Okay, so just put that over there so it can be seen. All right, so what I want you to do on your calculator, I want you to go into table mode. So scroll across. Has everyone got their calculator here today? Yes? Yep. Okay, so table mode is second row, third one along. You're going to go to table mode. Okay, and then into there. And so if you've got any functions in there, which I obviously do, then just delete them. I need to go back into y equals form. Okay. So you guys might be in parametric form, so just make sure you put yourself back into equation form. Are we okay? So we're in table mode, right? So what I'd like you to do is in the first equation, just type in the equation 9 minus 0.1 x squared. So 9 minus 0.1 x squared, execute. Pretty simple. Okay. Now we're going to set up our table. We're going to get the calculator to create the heights of each of those for us. Now, in this example, it's not hard to do the math. The math isn't difficult, but you only would be expected to do it in your calculator, so that's why we're going to do it that way. Okay? So if you'll see at the bottom of your screen, you've got set and table. So set is F5 and table is F6. So go into F5 first of all, because you've got to set your table up. So this table, we're going to start at x equals what? 2. I'm going to end when x equals 5. And what are my steps? So I'm going up in ones in this case. Yeah? So let's go up in 1, so my step is 1. Are we okay with that? Yep. Then we just exit out of there. So we set our table up first, and then now we've got our table set up, hit F6 for table, and there are our values. Are we okay with that? All right, so if I was to then, so I've got 8.6, 8.1, 7.4 and 6.5. All right, I don't know why that's so crooked. Let me just rub this out. Ah! I hate it when that happens. All right, so I need to rub out that. No. Let's go. No. Supposed to be like that. Okay, so if I'm going to work out the areas, the values I want are the ones on the left, yes? So the heights are going to be, so that's 8.6. What's the next one? 8.1 and 7.4. So that is 8.1 and that's 7.4. Now, I don't actually need this point on the right-hand end. Even though the table's given to me, I don't need it for my calculations, right? So if I'm going to calculate the areas, right? So the total area, so this is left end rectangles, right? Left end rectangles. My area is going to be 8.6 multiplied by 1. Now obviously we don't need to multiply anything by 1, plus 8.1 multiplied by 1, plus 7.4 multiplied by 1. And so if I add those together, 8.6, that's 16.7, 17.1, 24.1. Square units. Just correct, just double check my addition, please. Because I don't want to get a mistake. Yep, cool. Okay, now what can you tell me about that approximation of the area? Yep, what else can you tell me?
It includes a little bit artificial.
Yeah, so that means it's greater than the real answer. Is that okay? Is it reasonable to assume that that's greater? So that answer, so our actual area that we want is less than that number. Is that a reasonable thing to assume? Yeah? Okay, all right. So that's how we calculate left-hand areas. And if I want to make that a bit more accurate, what could I have done? No, more rectangles. Yeah, so we're staying with the, so we make more rectangles. So what I could do is instead of going all the way across in ones, I could go over in halves, right? And if I did that, so I'll do that in a completely different colour just to highlight what I'm talking about. So if I was to then split this rectangle into these little rectangles here, right, and then draw rectangles across, can you see that there's less area wasted? Like this, it's going to be a closer answer. Is that fair enough? Right. Okay. But in this case, when the graph is decreasing, right, when the graph is decreasing like this one, left end rectangles is always going to be a bigger value. Okay. If my graph is ever increasing, so if I'm looking at an area of an increasing graph, like this one, right, then left-hand rectangles, if I was to just do this quickly, then left-hand rectangles would look like this. Right? So this is the areas that I'm calculating. And you can see that I'm actually less than the actual area. So it depends on the direction of the graph, increasing or decreasing, as to whether left-hand rectangles gives me a bigger or a less value. Okay? So what if I thought, well, okay, that's left-hand rectangles. What if I did right-hand rectangles? Okay? So right-hand rectangles. Right? So what would be my total area this time? Okay? So what values am I going to choose now? Again, I'll go back to my original graph. So I'll get rid of the blue. Just does not like me. Right? If I was able to get rid of the blue, all right. So again, I'll just put my things back in. Okay. So the right-hand rectangles would be exactly the same idea, except this time I'm going to from the right-hand height. Is that okay? And so that's going to be 8.1. That's, was it 7.4 and 6.5? Is that okay so far? So this is what we call right-hand rectangles. Now, if I was to do this area, I'm not going to worry about multiplying by 1. 8.1 plus 7.4 plus 6.5. So what's that? 15.5, 16, 22. Okay? And so what I could assume is my actual area is somewhere between, oh, that's really bad writing, is somewhere between 22 and 24.1. Is that okay? And I can't, and the only way I can make that range closer is to increase the number of rectangles. And that would take more time. But in terms of using our calculators, whoops, wrong one. That would just simply mean when I go into my setup, instead of going across in ones, I might go across in halves, or I might go across in quarters. I just have a lot more numbers to calculate. Okay? Now, I'm hoping that you can appreciate that that's not very accurate. Is that fair enough? Right? So what we're going to do then is say, all right, well, if that's not very accurate going in rectangles, how can I make it more accurate? And that's where I bring in trapezoids. Okay? So this is where I'm going to bring in what we call the trapezoidal rule. Okay, so instead of making rectangles in between each of my points, I'm going to make trapeziums. Okay, and so what would that look like? So let's go to here. Okay, and let's do it with our question that we started with. I'm just going to rub this bit out. I'm still going to go to 5. Ooh. Okay, so I'm going to go back to this function, e to the t. And I want to know what the area is between 0 to 5. Okay, so I'm going to go in nice easy increments. 1, 2, 3, 4. So again, please assume that they're evenly spaced. All right? And what we're going to do is we're going to create trapeziums. Okay? So my trapezium number 1 is going to be there, so that's going to be trapezium number 1. And trapezium number 2, trapezium number 3, trapezium number 4, and trapezium number 5. Now, even with my very dodgy diagram, all right, if I zoom right in, we can see that much better approximation of the actual area. Not perfect, because trapeziums have a straight side, whereas this is a curve. So it's not perfect, but it's a lot better. Okay? And so what we're going to do is we're going to see if we can work out the area using trapeziums. Is that okay? So let's do that. So first thing we're going to do is we're going to give ourselves a bit of a head start by using our calculator to work out the heights of each of these. Now, to make life simple, we're going to go to 1 decimal place. Okay, now being e to the power of something, you're going to get a screen full of decimals. But just for the sake of this, because I don't want to be writing numbers till tomorrow, we're just going to go to 1 decimal place. So use your graphics calculator. See if you can remember what we just did with the previous example. How could you set this one up so you get a table of values that tell you the heights of each of those trapeziums? So each of the sides of each of those trapeziums. Yes, so the formula is, there it is. So it's v equals e to the t. So we, in our calculator, we go y equals e to the x. And again, just write the heights down to 1 decimal place. Not very accurate, but for the sake of this activity, it's plenty. So you put your function in, and then you set your table up. Is the expectation you can do this in your exam? Yes. Is there a question on your exam that requires you to do this skill? Yes. Could I be any more clear than that? No. Apart from giving you the question, which I'm not going to do. I like my job. So my starting point is 0, my end point is 5, and I'm going in ones. My eyes are pretty bad. Are those the right numbers? 1, 2.7, 7.4, 20.1, 64.6 and 148.4? This is what I'm saying. I couldn't see if it was a 5 or a 6. My eyes are that bad. So is it 54.6, is it? Thank you for the correction. Yep. It's just I couldn't literally read if it was a 6 or a 5. Hence the reason I was asking. If I had my glasses on, I could see it, but I've got my lenses in and then I'm bugging. Okay, so we're all okay how we got those numbers? Did you get them okay? Setting up your calculator, yeah? Yep. Okay, because you will need to know how to do that. So that's why we keep practicing. Okay, so what we're going to do now is we're going to calculate the area of each of those trapeziums and then add them together. All right, now this, as you can imagine, is going to be a little tedious. Okay, so if I was to add up each, so the area and what the point of what I'm getting to is there's a formula to help us with this process, but it doesn't make the whole thing easier, it just makes it a little bit quicker. So let's look at area number 1. So we've got the total area is going to be, so what is the area, if you're going to write the formula out for the area of the first trapezium, what would it be? It's going to be a half multiplied by so it's going to be 1 plus 2.7 multiplied by 1, which is the width of the triangle. So what I'm going to do for the sake of it, I'm going to put the width at the front, okay? I'm going to put the half and the width at the front, and then I'm going to put the brackets there. Is that okay with everyone? So I'm just going to, and as I said, please bear with me, all right? Again, it's going to be exactly the same, and then it's going to be 2.7 plus 7.4 plus a half times 1 times 7.4 plus 20.1 plus a half times 1 times... Now, you don't have to roll this out if you don't want to, because I've got it I'm doing it for you, but there's a method to why I'm doing this. Plus half times 1 times 54.6 plus 148.4. Okay, so there we go. So there it all is there. So there's my calculation to find the area. I'm not actually going to work it out for the minute. We will in a minute, but first of all, so we've got half times the width times the sum of the parallel sides, half times the width plus the sum of the parallel sides, one away else. Okay, so because we're all good mathematicians now, we're all being year 12, right? Can you see anything common across this board there? Is there any common factors we can see in each of those terms? I reckon there might be. I don't know, but what about the half and the 1? Well, yeah, but I want to keep the 1 there because what we're trying to do is develop a formula, right? So what does the 1 represent? It's the width, right? So I've happened to chosen, the width. So I've happened to chosen the width to be 1 for this example for the sake of ease, but I'm going to leave it there because I want to replace it with a variable later, which is the width, okay? So that's why it's there. Okay, now, I'm not going to write out all the brackets again. Let's have a look at what we actually see before we go any further. So let's have a look at I'm going to move away, sorry people on the recording, but I'm going to go to the board. Okay, so look at what's inside the brackets. Now, just focus on what's inside the brackets. What do you notice? Right. Can you see that some of the widths are there twice and some of the widths are there once? Can we all see that? So we're just focusing on what's inside the brackets. We can see that some of the numbers are there twice and some of the numbers are there once. Which numbers are there twice?
Anything that's not on the edges.
Right. So the number... So any of the middle ones, right, the 2.7, 2.7, 7.4, 7.4, 20.1, 20.1, 54.6. The ends, right, that one and that one only appear once. But it's only in one, those ends are only in one trapezoid. The first one and the last one. Whereas each of the middle numbers are on 2 trapezoids. They're on the left hand and the right hand, whichever way you're looking at. Okay, so the 2.7 belongs to that trapezoid and the one beside, all the way across. So we can shorthand what we see there, right? And if I was to write all of those out, right, I'd have 1 plus the 148.4, because they just appear once each, right? And then I've got 2 lots of 2.7 plus 7.4 plus 20.1 plus 54.6. close brackets. Can we see that? Yeah? Okay, so what I've got there is I've got a bit of a shortcut to writing this whole thing down. Okay? We're going to call this the ends. Hopefully there's a good reason, that's pretty obviously why. What do you reckon we're going to call these? The middles. Okay, so we've got ends and we've got middles. Okay, and so what we're going to do tomorrow, yes, we're double tomorrow, what we're going to do tomorrow is continue with this development of this formula. You've got homework to do, it's called your PS&T, right? So I'm not going to give you anything to do tonight, we'll continue working with this tomorrow. All right?